A pair of random variables. In this video, we will talk about two variable uh, probabilities. So first of all, let's have a look at difference between joint and conditional probability. Joint probability is when both events A and event B happen simultaneously. For example, the probability of drawing a card that is red and also a king is 2 by 52, which is equal to 1 by 26. The reason is that there are two red kings in a 52 card stack. Whereas conditional probability is when an event depends on another event. It means that event A happening given that event B has already occurred. Suppose a player wants to draw two hearts, and suppose in the first attempt the player draws a heart. Now the player wishes to draw a second heart. Since one heart has already been chosen, there are now 12 hearts remaining in a deck of 51 cards. So the conditional probability of P draw of second heart given that first card is a heart is equal to 12 by 51. So in this case, the probability of drawing a heart depends whether it will change according to the result in the first attempt. If in the first attempt the heart was not drawn, then the probability in the second attempt will say 13 by 52. But if heart was drawn in the first attempt, then the probability will be 12 by 51. So it depends what was the result of the first event. The joint probability function describes the joint probability of some particular set of random variables, and it is expressed as probability of a1, a2 up to an. Thus, an expression of P probability, height, and nationality describes the probability of a person has some particular height and has some particular nationality. As we know that different nationalities have different average height. So here height depends on the nationality as well. Therefore, P height is equal to 175 centimeter and nationality is Australian is equal to 0.5, means there is 0.5 chances of a person picked from a population is an Australian and has the height of 175 centimeter. Actually it should be 175 centimeter. So the joint cumulative distribution function of random variables x and y is given as probability of x and probability of y, given x is where x is less than equal to smaller x. The joint CDF is a complete probability model. The joint probability mass function of discrete random variables x and y is P x is equal to x and y is equal to smaller y. There are 940 wafers in a semiconductor. This is an example of joint probability example. There are 940 wafers in a semiconductor manufacturing process. Suppose one wafer is selected at random. Let H denote the event that the wafer contains high levels of contamination, and C denote the event that the wafer is in the center of a sputtering tool. So sputtering tool is a tool which deposits a metal on some substrate, and this is called sputtering tool. What is the probability that a selected wafer is from the center of the sputtering tool and contains high levels of contamination? So here this table is given where we have got contaminations given on the left hand side and location in the sputtering tool is given over here, center and edge. So for example, a low probably number of wafers which have got low contamination and have got in the center of the sputtering tool is 514, whereas wafers having low contamination but are on the edge of the sputtering tool are 68. So total altogether it is 582. So similarly here, wafers having high contamination and in the center of the sputtering tool are 112, and wafers having high contamination but on the edge of the sputtering tool are 246. So altogether low contamination wafers are 582 and high contamination wafers are 358, whereas total of wafers in the center of the sputtering tool are 626 and wafers on the edge of the sputtering tool are 314. So what we are asked over here is that what is the probability that a selected wafer is from the center of the sputtering tool and contains high levels of contamination. So first of all, we see that this is the number of wafers in the center of the sputtering tool, and the second thing is this contains high levels of contamination. So it means this is 112 because high contamination and center is here. So 112 divided by 940, which is the total number of wafers given, so the probability is 0.119. So we can see that it is nothing but the intersection of H and C. Joint probability over here is simply the intersection of H and C. There is another example. An urn contains 4 red, 5 green and 6 blue balls, and 3 balls are taken at random. Given the number of red balls represented by the random variable x and the number of green balls by the random variable y, we want to find the joint probability where k ranges from 0 to 4 and m ranges from 0 to 5. Find the joint probability f of x. So first of all, we will find the total number of balls in the space. Actually it is not points but the balls. So it is 4 plus 5 plus 6, so altogether it is we have got 15 balls. And how many balls we are going to draw? 3 balls are taken at random, so k is equal to 3. So n is equal to 15, which is the total number of balls, and k is the number of samples or number of draws, which is equal to 3. So first of all, to find the total number of possible points in a sample space, we take binomial coefficient of 15 and 3. So the formula is very simple. 15 factorial divided by 3 factorial means n factorial divided by k factorial, n minus k factorial. So 15 minus 3 factorial, which is equal to 15 over 2 factorial divided into 12 factorial, and altogether we get 455 such possible combinations. So the number of ways in which 3 balls can be picked from 15 balls is to choose k balls from red balls, m balls from 5 green balls, and 3 minus k minus m balls from 6 balls. This is very simple because as we have seen that we just simply multiply the probability of or number of ways for each ball. For example, for we have to pick the 3 balls from 15 balls, and we have to choose we can choose k balls from red balls and m balls from 5 green balls. This is given over here. We want to find the joint probability p of x y or k comma m, where x is equal to k and y is equal to m. So hence the probability is very simple. C4 comma k, all the combinations of C4 4, given that we have to pick 3 balls or whatever the k number of k's is there, or C is equal to 5 comma m, and this C is simply what the you may say that if no green ball, or sorry, red ball or green ball is chosen. So this is, you may say, this is the total possible combinations for blue balls. 6 blue balls are here. So of course, for example, if you have not chosen any green ball or red ball, in that case here all the 3 balls will be blue balls which we will pick. So in that case k and m will be 0. So first of all, we find for px y 0 comma 0, where we are assuming that 0 comma 0 means that neither red ball is picked nor the green ball is picked. So in that case what we find is that, as we expected, that all the 3 balls are blue balls. 6:3, 4 0, 4 0 representing red balls, and 5 0 is representing green balls, because we have got 4 red balls and 5 green balls over here. So we have simply put over here k and m, and here sorry, k and m is over here, and here we have got put this total number of red balls and green balls, or you may say x or y. So what we get, divided by 455, because this is the total number of balls. So here we get, take 6, this binomial coefficient of 6 and 3 is 20, 4 0 is 1, and 5 0 is also 1. So that is, it is equal to 20 divided by 455. In case of 0 and 1, it means that no red ball is chosen, but at least one green ball is selected out of 3. So in that case we have got the same way we have calculated, it is equal to 75 divided by 455, and then 0 comma 2 and 0 comma 3. In the same manner, you can pause the video and can see that how these calculations are done. And after that, what we get this table over here, which shows all the possible combinations of km, and where, for example, we have got both. It means k is equal to 0, m is 0, means neither red ball is chosen or green ball is chosen. Here we have got 3, it means this is not possible, because if you have chosen 3 red balls, because total you have got to pick 3 balls. So if you have to pick 3 red balls, then you cannot of course pick the green balls at all. That's why it is given 0 over here. So wherever you see this 0 over here, it means that this combination is not possible. Possible combinations are these: 0 0, 1 0, 1 1, 1 2, but 1 3 is not possible. It is more than 3. Altogether you have to pick only 3 balls. So if you have picked 3, it is not possible that you pick 3 green balls and also pick a red ball. This is not possible. So, and we will talk about this total over here in coming slides. Up to this, if you just look at this table from here to here, you will find that all the probabilities for all the possible combinations of k and m. Another example of a joint probability: 2 ballpoint pens are selected at random from a box that contains 3 blue pens, 2 red pens, and 3 green pens. You can see that this example is very much similar to the last example, only the thing is that now we are talking about pens, and instead of balls, and the number of red pens and blue pens and green pens have changed. So if x is the number of blue pens selected and y is the number of red pens selected, find the joint probability function f x comma y. Again we will do the same thing. We will first find the total number of pens, which is equal to 3 plus 2 plus 3 is equal to 8, and here k is equal to 2 because we are going to pick 2 pens in this case. 2 ballpoint pens are selected at random, so k is equal to 2. In this case, the total possible pairs of values is 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and 2, 0. Why is that so? Because the total number of ball pens is 2, so we cannot have any such combination where the total number of ball pens which we are going to pick exceeds 2. So again we will use the same formula over here, but this time this value will change, because here we had 6 blue balls. If red and green are not chosen, then if we are going to pick all the 3 balls, then we had to pick all the 3 balls from the 6 blue balls. But over here x is representing blue ball pens and y is the number of red ones, and we have got 3 green pens. So in case of 0, 0, what we have 2 minus x minus y. There we had 6 minus k minus m. It doesn't matter whether you call it k or m or x or y, it is the same thing. But the important point is that this number has changed. There it was 3, here it is 2, because there you had 3 draws, here you have got only 2 draws. So 3 and binomial coefficient n k, 3 is n is equal to 3, k is equal to 2, n is equal to 3, k is equal to 0, n is equal to 3, k is equal to 0, because we have got 3 blue ball pens and 2 red pens. So this one is representing the blue ball pen and this one is representing red ball pens. And again the same way we have divided by 28, which is the total number of ball pens, and we get 3 divided by 28 for f0, 0. For f0, 1, same way we have calculated, it is 3 divided by 14, and for f0, 2 it is 1 divided by 28. So in this table you can see that what is the probabilities for each combination. Here again this 0 over here is representing that these combinations are not possible. You cannot have 2 comma 2 means 2 red ball pens and 2 green ball blue and red, sorry, 2 red ball pens and 2 blue ball pens. This is not possible, because in that case altogether it will become 4, and which exceeds the total number of possible picks. Marginal PMF. In an experiment that produces 2 random variables x and y, it is possible to consider one of the random variables y and ignore the other one, x. When a random variable x is part of an experiment that produces 2 random variables, we can sometimes refer to its PMF as marginal probability mass function. This terminology comes from the matrix representation of the joint PMF. By adding rows and columns and writing the results in the margins, we obtain the marginal PMFs of x and y. So for discrete random variable x and y with joint PMF p x comma y is the value of x and y, so it is simply the sum of all probabilities of x and y, and p of y is the sum of all the probabilities of x comma y. So as I told you before that, we will talk about these values over here, these sums over here. These are called marginal PMFs, because here you can see this 165 by 455 is actually the sum of these all values of k when k is equal to 0. Here if k is equal to 1, then the total is 220 divided by 455, which is simply 60 plus 120 plus 40. And then this if k is equal to 2, then 36 plus 30, it gives you 66 over 455. So if this example, you can see if you are asked to the probability of 2 red balls, you are just interested in how many red balls are picked. So picking up 2 red balls is 66 over 5. And probability of 3 green balls is equal to 10 over 455 over here. Now, 2 variable applications. There are many situations in which we observe 2 random variables and use their values to compute a new random variable. For example, we can describe the amplitude of the signal transmitted by a radio station as a random variable x. We can describe the attenuation of the signal as it travels to the antenna of a moving car as another random variable y. So x is representing the transmitted signal and y is representing the received signal. In this case, the amplitude of the signal at the radio receiver in the car is a random variable w is equal to x divided by y. So what is the amplitude of the received signal depends on the transmitted signal, the amplitude of the transmitted signal, and the attenuation of the signal, transmitted signal. So x divided by y represents the received signal w. Other practical examples appear in cellular telephone base stations with 2 antennas, which is called MIMO or MIMO. The amplitudes of the signals arriving at the 2 antennas are modeled as random variables x and y. So here we have got multiple antennas which are transmitting, and in that case this x and y are representing 2 different signals or 2 different amplitudes of the signals arriving at 2 antennas. The radio receiver connected to the 2 antennas can use the received signals in a variety of ways. It can choose the signal with the larger amplitude and ignore the other one. In this case, the receiver produces the random variable w is equal to x if x is greater than y and w is equal to y otherwise. This is an example of selection diversity combining. The other way is that the receiver can add the 2 signals and use w is equal to x plus y. This process is referred to as equal gain combining because it treats both signals equally. And the third way is that a third alternative is to combine the 2 signals unequally in order to give less weight to the signal considered to be more distorted. In this case, w is equal to ax plus by. Here we are using these weights a and b to optimize the received signal, or in that case the receiver performs maximal ratio combining. All 3 combining processes appear in practical radio receivers.